Mr. Cannabis.
The concentration of dissolved oxygen in water is influenced by several factors, including water temperature, salinity, and atmospheric pressure. The relationship between water and temperature is inverse, meaning that cold water can hold more dissolved oxygen than warm water. The table typically shows dissolved oxygen values representing the saturation for the corresponding temperature. The amount of dissolved oxygen in water is usually measured as milligrams per liter or parts per million, which are equivalent. This value can be converted into a percentage by dividing by 10,000. However, the percentages usually work out to very small numbers, so using milligrams per liter or ppm is preferred. According to a study conducted by an agricultural researcher, arugula plants' growth and nutrient status were significantly affected by different dissolved oxygen levels. At a low rate of 2 ppm, the arugula plants were severely stunted and unsaleable, with severe nutrient deficiencies. At a moderate rate of 7.5 ppm, the arugula looked normal with slight deficiencies. At the high rate of 29 ppm, the plants almost doubled in size and there were no nutrient issues. The researcher also observed different root growth patterns for crops at different dissolved oxygen levels. At the low rate of 2 ppm, the roots were short and stubby and seemed like they were almost retreating from the water, remaining mostly in the rock wool rooting cubes. At the moderate rate of 7.5 ppm, the roots were long and had a lot of lateral branching, resembling standard hydroponic roots. At the high rate of 29 ppm, the roots had less lateral branching, but they were white, long, and thick. It seemed that since there was so much oxygen in the water, the plants didn't need to have so much lateral branching. Dissolved oxygen is not just an additional nutrient that contributes to plant health. It can have direct economic impacts as well. When used appropriately, it can reduce the amount of nutrients and micronutrients required, as well as the amount of costly chemicals such as fungicides. This is because healthy roots are more efficient, meaning that nutrients can often be uptaken quicker than they can be flushed out of your growing medium. This increased root health also helps them resist disease and pathogens. In hydroponics, evidence suggests that plant growth increases with supersaturation levels of dissolved oxygen, reducing cropping times and increasing fruiting and flowering yields. The same study also revealed, when comparing 7.5 ppm to 29 ppm, that on average, all crops grown with the 29 ppm were at least a week faster to finish to marketable size. Now, for those of you looking at the DO chart and wondering how they got 29 ppm when water can only have 15 ppm at the freezing point, well, oxygen supersaturation. Oxygen supersaturation occurs when more oxygen is dissolved in a sample of water than would be expected if the water were oxygenated using normal air. During oxygen supersaturation, oxygen displaces other dissolved gases such as nitrogen. This can be achieved by having your air pump placed in a high oxygen environment. Improving levels of dissolved oxygen can be achieved through various methods. Simple aeration or agitation of the water can increase dissolved oxygen enough to prevent problems. Injecting air, or particularly as we mentioned, pure oxygen, can increase those levels as well. Paying attention to temperature can also improve dissolved oxygen levels, as again, colder water can hold on to more oxygen. But as I mentioned in section 5.10, I don't advise releasing substantial gases directly into the root masses due to mechanical agitation. However, if you're using a bucket system or table setup, which I've done myself, or you can't really avoid releasing directly into the roots, I would suggest using a fine as possible bubble wall or run the lines between your plant rows or the exterior of the bucket to minimize the disturbance of the root zone.